Welcome to another Maths Talk. Today we have with us Aritrabha Majumdar, a B1 second year student. He is interested in probability theory. Today he is going to talk about random walks.
Thank you very much, Artupio, for the introduction. So today in this talk, we are actually going to observe what a random walk really is. We will define it formally, and after that we will talk about its convergence and divergence. Okay. So first of all, what is really a random walk? Let us consider the line of all the integers. In the center we have 0, here we have 1, 2, and other positive integers, and here we have the negative integers. Okay. So let's take a bug is standing at the origin. Okay. At each moment, the bug tosses a coin. If head comes, the bug decides to go to the positive direction, and if tail comes, the bug decides to go to the negative direction. Okay. So let's say the first result is head and the bug goes to 1. After that, again a head comes and the bug goes to the point 2. After that, again goes to 1. Then again a tail comes and it reaches to the origin again. Then again a tail comes, it goes to -1. And after that, it again returns to the origin. Okay. So if we try to plot a graph where this axis represents the time and this represents the position of the bug after each time interval, then the bug starts at the origin and the very first second it goes to 1. After that it goes to 2, then again back to 1 to 0, and then again -1 and again to 0. So this is one of the possible paths the bug could have taken when he moves, when he starts his journey at point time is equal to 0 and goes to the very end. Okay. So this is, till now this is just a basic idea that we have actually visualized how a random walk can look like. But to explore the more of these properties of such random walks, we need to define it formally. So, to define it formally, let's consider the sample space omega sub n, which is basically collection of all omega 1, omega 2 until omega n, and this belongs to -1, 1, whole power n, this set. Okay. So basically each step you are taking, that is basically composed of either +1s or -1s, right? So after many steps, every step you have taken, if we write that in order, that is basically a binary sequence of +1s and -1s. Okay? And we also write that x sub k of omega is equal to omega sub k. That is the step taken at the kth time by the random walk or the random walker. Here we will use the walk and walker interchangeably. Okay. So x sub k of omega denotes the step taken at the kth moment. Okay. So after time n, if we want to denote the position of the random walk, then it is given by summation of k starting from 0 to n x sub k of omega. Basically, you sum up all the steps from the very beginning to the nth time, and then you get the final position of the bug. Okay. Nice. So now for all omega in this particular set, we get a trajectory of length small n. Okay. So under this capital omega sub n, we are having a set of random variables given by x sub n, where n starts from 0 and goes up to capital N. Okay.
N equals to 1 when we start from 1.
No, if we start at 0, we are defining it. We are defining that at the origin s sub 0 is equal to 0, the probability is 1.
I mean, what is x0 omega then? What is x0 omega?
For x0 omega, we will just define it to be 0. For x0 omega, yeah, for the purpose of the definition, if we want to make it consistent, we will just take x sub 0 of omega to be 0. Okay. And in this particular case, we haven't introduced any kind of bias in the random walk. That is, the bug is just tossing a coin. The probability of getting a head and tail both is half. So, the probability distribution induced on this omega sub n is actually a uniform distribution. And for any subset A of this omega sub n, probability of A is actually cardinality of A divided by 2a to the power n. Okay, so this is our probability and this is our total sample space, and taking these two together along with this random variable, we have a complete probability space, and by that we can define a simple random walk of length n. So what is the formal definition of a random walk of length n? The sequence of random variables Sn on the finite probability space omega sub n along with the probability mentioned p is known as a simple random walk of length n. And in all these random walks, the increment is actually independent. And by increment, what I mean is, suppose you take s sub k minus s sub k minus 1, and you take s sub k minus 1 and s sub k minus 2. These two increments are basically independent. And I am actually claiming even a stronger statement that for any m and n in the natural numbers, x sub n and x sub n will be independent. Okay, so basically any two step in this random walk will be independent, right? Now we will evaluate the probability that Sn is equal to x. Okay, so basically after n many steps or after n unit of time has passed, what is the probability that the random walk is standing at the position x? Okay. Now the random variable xn, which is denoting the step taken at the nth time, that follows Ryder-Master distribution with probability 1 by 2. What does it really mean? That it takes the value plus 1 in probability half and it takes the minus value in probability half as well. So if this happens, then we can write okay, and after that we have x sub n plus 1 by 2. That is basically my say n starts at 0 and it goes up to some, let's say, what can I say, k. So the random walk, the position of the random walk after k many steps plus n by 2, that follows binomial k comma 1 by 2, because sum of binomial is binomial, so easily we have this thing. So now this will help us to evaluate this probability. So probability of s sub k is equal to s
plus k. Sk plus k.
Oh. So this probability is actually now given by a choose k choose k plus x by 2 divided by 2 to the power k. Okay, so basically this is the binomial distribution that we are taking k plus x by too many steps in the plus 1 direction, and then after simplification we get this thing. Okay. Now what happens if k is even? Okay, Let's consider the case where k is even. If k is of the form 2m, then we can write this probability is equal to 2m plus x by 2 to power k, and k is equal to 2m, that we already know. Now an interesting thing is, if we take an even number of steps, then the position of x should be even. Why? Because after taking even number of steps, the random walk can't really stand in an odd position, because that will basically make a contradiction. So, what is the mode of this distribution? So, for which x, basically this probability is maximized. And from this construction, it is fairly obvious that if we take x equal to 0, then the probability is 2m choose n 1 upon 2 raised to the power k. Okay. So for a one-dimensional random walk, the probability that after k steps the random walk is at position x is maximized for the origin, and not for only one-dimensional random walk. We will later see that it is true for actually random walk in any dimension. Okay. So now we will approximate this thing for large case, or in this case where k tends to infinity. So we have probability of s sub k is equal to 0, and we will just expand this 2m choose any term, and we will get 2m factorial divided by n factorial square, and after that we will apply the Stirling's approximation that I have already written on that board. And after doing the simplifications, what we will get is, this is almost similar to 1 by square root of pi. Okay? And this is a very interesting result which was proven by George Polya, that for any d-dimensional random walk, the probability that it will eventually return to the origin after n many steps is actually equal to big theta of n power minus b/2. Okay, where b is the dimension. So now we can see that this already holds for the one-dimensional case, because this is basically in raised to the power minus half and b is equal to 1, so that holds. Okay, and now we will extend the definition of this one-dimensional random walk to multiple dimensions, and then we will kind of intuitively see that those properties also hold in any d-dimensional random walk. So before defining the random walk in d-dimension, we consider the usual L2 norm along with we write the expression. This is the usual L2 norm which we will consider. Okay. And for any given from the set of natural numbers, we write omega sub n is equal to all those omega such that omega sub k, I mean the kth component of omega, is actually a member of the d-dimensional grid, and the L2 norm of omega is actually equal to 1. Now why this part is significant? The L2 norm of omega is equal to 1 basically implies that at each step the random walk can only move in one of the possible 2D directions. Like in the case of Z2, if we consider this point to be the origin, the random walker has 4 possible directions to go. Okay, and this particular property ensures that we will only consider all those omega sub k's in all those omega sub k's which basically denote that the bug at any given moment only moves in one particular direction, like only to the upward, downward, or left or right. Okay. We are basically restricting moves of this kind, because in moves of this kind the value of omega, the norm of omega sub will be equal to root 2, and we are restricting all those cases. And again in similar fashion, the position after time n is given by x of omega when we start from 0 and goes to n. Okay, and by definition we define that x sub 0 of omega is equal to 0. Again we have a uniform distribution, and for any a which is a subset of this omega sub n, we have probability of a is equal to the modulus of a divided by 2a divided by 2b raised to the power n. Okay, so basically the same thing we had in the one dimension, we are extending it to a d dimension. Everything remains the same, just the set looks a bit different, and this particular Sn in this case is now basically a d-dimensional vector which will look something like this. It has d-many components, and all of the components move kind of randomly. Okay. And now we have defined the random walk for d-dimensions as well, and we will talk about the recurrence of transience, recurrence and transience of the random walks. So before talking about recurrence and transience, let me define a new term which is sigma sub 0, or rather we will talk about sigma sub a. This is minimum of all those natural numbers such that at the nth step the random walk is present at the point A. Okay. Now let's see what our sigma sub 0 is for the case we have described earlier. So if we want to talk about sigma sub 0 in this case, the random walk returns to the origin at two points in time. Okay. And by sigma sub 0, we will consider this point only, the first return to the origin. And we say that a random walk is recurrent if the probability that sigma sub 0 less than infinity is equal to 1. Then we see that a random walk is recurrent, otherwise it is transient. Okay? And before showing that any random walk is recurrent or transient, we will do an important lemma which will help us to decide whether the random walk in one dimension or two dimensions or any other dimension is transient or not. So first of all, we start by claiming that probability of Sn is equal to 0 is equal to summation of I running from 1 to n into sigma sub 0 is equal to I times probability of S sub n minus I is equal to 0. This is basically a total probability which is obtained by conditioning on all these sigma sub 0s. Right? So basically we apply the conditional probability that at first the random walk returns to the origin at the ith time, and as the random walk at the end of the day returns to the 0 again, in the remaining n minus I many steps, it has to return to 0 once again. Okay? And now we define two generating functions. One of them is and another generating function is okay. So these are my two generating functions. And for these generating functions, the motivation behind this generating function actually comes from the random of Green's function. And the random of Green's function is actually defined by g of x comma 1, so that is nothing but n from 0 to infinity probability of x is equal to x. Okay. Now if we rewrite this in a different form, this probability is basically the expectation of the indicator random variable that is presently x or not. Okay, and by the linearity of expectation, we can just pull it out, and it will look something like this. So the random of Green's function basically gives us the expected number of visits to the point x. Okay, and now in this particular g of 0 comma z, we will plug this value in, and we will try to establish some relation between g and f. So we have is equal to 0 to infinity, or instead of starting from 0, let us start from the point 1. And for n is equal to 0, this thing will be z power 0 times something, so that is basically 1. So we have 1 plus n is equal to 1 from infinity, z power n. I running from 1 to n. Probability of sigma is equal to I times probability of this is minus I is equal to 0. Okay. Now let's take this z power n inside, and we take this inside. We can write here z to the power I, and here we can write z to the power n minus I. Okay. And after that, plugging everything together, what we get is, for all I belong to a set of natural numbers, this is z power I, probability of sigma of 0 is equal to I, times all is very close to natural numbers. Basically, I am taking this n minus I to be my j, and from j belongs to all natural numbers, along with 0, z power j, probability of is sub j is equal to 0. So basically, this we obtain from the Cauchy product, and then we can divide this entire thing as 1 plus f of 0 comma z times g of 0 comma z. And after some simplification, we can write this thing as this is an important relation between f and g, which will help us to determine the recurrence and transience. So first of all, let us take the case. Let us take the case where g of 0 comma 1, that is basically starting from 0 to infinity, probability of x of infinity 0 is finite. The case where g of 0 comma 1 is finite. Okay, what happens in that case? If g of 0 comma 1 is finite, then we can clearly see that from this relation, if this thing is finite, we have f of 0 comma 1 is equal to 1 minus something we have here, and that is essentially less than 1. And now what is my f of 0 comma 1? F of 0 comma 1 was actually summation n equal to 0 to infinity probability of sigma sub 0 is equal to n. And again, this thing is actually equal to say the random walk in this case is transient. So if G of 0, 1, but the solution of all these probabilities is finite, then in that case we have that the random walk we will have will be transient. I mean that we won't introduce the origin anymore. Okay? And if this sum is divergent, then obviously we have already guessed that the random walk will be recurrent. But how can we prove that recurrence? So if this thing is equal to infinity, then what we do, we fix our epsilon greater than 0 and another insert epsilon from the set of natural numbers. Okay? And after fixing them, we have solution of n starting from 0 to insert epsilon. Solution of n is equal to 0 is greater than equal to 2 by epsilon. Okay. Now we take z sufficiently close to 1, and after taking z sufficiently close to 1, we can say that for all n instead of natural numbers, z power n will be greater than equal to 1 by 2. Not for all n. Okay, at least for all n greater than say n power epsilon. Less than n power epsilon. That thing will happen. So from now we have this relation, and from there we can say that 1 by G of 0, that is given equal to 1 upon everything A1 from 0 to 1 z power n probability of epsilon is equal to 0, and we have already shown that this thing is greater than equal to 1 by epsilon, so this entire thing is greater than equal to epsilon, and as our epsilon is arbitrary, this thing is equal to 0. Okay? And from that part, we can actually write f of 0, 1 is equal to limit z approaches to 1. So 0, z, that is equal to 1 minus limit z approaches to 1 and then 0, z, and we have already seen that this thing is equal to 0. So in this case, this is equal to 1. So when this particular sum is divergent, this f of 0, 1 is basically my probability of sigma sum 0 is equal to 1. So in that case, the random walk will be recurrent. So in the first dimensional case, one-dimensional case, and we have already seen that probability of epsilon is equal to 0 is almost equal to 1 by square root of pi, right? So let's take solution on both sides and evaluate this 0, 1 for one dimension, and that is equal to this solution, and we know that this sum diverges. As this sum diverges, we have probability of sigma of 0 less than infinity is equal to 1. So the random walk for one dimension will always be recurrent. So it eventually returns to the origin, but there is a special property that the expected value of the time for which it returns to the origin is actually infinity, and we call that random walk null recurrence. That is the interesting property of this conventional random walk. And now let's go back to the Paulia's theorem once again. So by Paulia's theorem, for any random walk in ZB, if we try to come at this thing, what we have is minus d by k. And this sum will be finite or will be convergent for all b greater than equal to 3. Right? So from this part, so for all b greater than equal to 2, we know that this sum will be finite or this sum will be convergent. Okay. So for random walk in the three-dimensional integral lattice or four-dimensional integral lattice, the probability of random walk returning to the origin will be less than 10, or we can say that the random walk will be transitive. Okay. So the proof of the random, so basically the conclusion here we can say is for simple random walk in the three-dimensional integral lattice, it is recurrent when we have dimension 1 and 2, and otherwise it is transient. Okay, so for all dimensions we are able to see the random walk will be transient. But this proof is actually kind of weak, I would say, because we haven't really checked whether this theorem given by Fourier holds for every direction or not. And if we really want to check that, we will have to do a lot of we will have to give a lot of combinatorial arguments, some bounds and stuff, and the calculation gets really risky. So now my aim is to present a more rigorous and more clear analytic tool that for all dimensions greater than equal to 3, the random walk will be transient. Okay. So first of all, we will define a probability measure on this case of three-dimensional random walk. And that particular probability measure is given by 1 by 2d indicator of norm x is equal to 1. Okay. We have already seen this that if norm x is equal to 1, then the probability that at every moment the above or the random walk of possibility any one of the available 2D options is basically safe because we have an individually bias, so the probability is 1 by 2D, and here we have individual. We have the individual. Okay. And we know that for every probability measure, we always have a unique characteristic function. And that particular characteristic function is basically given by some different e power I, that is the corresponding random variable, let us say x, and k is equal to function e to the power I k x. Yeah. So this will be my particular characteristic function, and for this given probability measure, this characteristic function is always equal. Okay. And now we will kind of retrieve this particular characteristic function by using Fourier inversion formula, and the Fourier inversion formula is this. Okay. Now our aim is to see that how this characteristic function really looks like. Okay. And my claim is the characteristic function in this case will be because let's take the one-dimensional case, and when d is equal to 1, this particular characteristic function will be this. This is the formula for the characteristic function, and we have the probability factor half for each of the steps to the +1 direction or -1 direction. And this is equal to this by A, and this is equal to cos of A. And after that applying induction, you can easily show that for any dimension this will do something like this. Okay. So now we are going to go. So now that geometric function when you give from 0, your 0, comma z, this thing will be something like, and which is for this probability of A is equal to 0, we basically put this entire value for the probability measure and get it and then raise to the power d, the integral of the base, and then everything again this time. Okay. And then after doing some rearrangement and stuff, this job will look something like integration with power phi of k whole power n. Now why we have phi of k whole power n? Because I have already said that for any q and n probability of natural numbers, two steps taken are basically independent. Okay. So the random variables in this case are identical and independently distributed. So when we are considering the sum of them, we will take the convolution of the corresponding characteristic function. So from that we have I k to the power n. Okay. And what was our topic of interest? Our topic of interest was 0, 0, 1. Okay. So what will that look like? Now basically we have interchange now the summation and the integral sign, and inside we have infinite geometric series. So that geometric series will be something like 1 by 1 by z and phi of k. And after we put z is equal to 1, the thing we are going to do is this integral times dk of 1 minus 5 plus. So we have already shown that the random walk is recurrent if and only g of 0, 1 is infinity, right? So g of 0, 1 is less than infinity if and only this big integral is greater than infinity. And our aim is to show that this big integral is less than infinity for d greater than or equal to 3. So basically for all dimensions equal to 3 or more than 3, the random walk we will have will be transient. And to prove that I will introduce a bound. 1 minus cos of k shield is equal to k square by 2 divided by equal to 2 square by pi square. Okay. So these bounds we can easily infer from the Taylor expansion. And after getting those bounds, whatever we do is basically take summation at both sides. So we have defined pi square kj square divided from 1 to b. This is equal to b minus summation of cos kj, which is equal to 1 by 2 summation kj square. And let's divide every side by b. So here we have 2 by b times pi square. This k is basically norm of k square. That is equal to 1 minus 1 by 2 cos of kj. That looks like 1 minus 5k, because we have already defined 5k to be 1 by d summation cos of kj. And here in this side we have 1 by 2b norm of k square. Okay. So now we will just take the reciprocals and integrate both sides. So here divide pi square. Divide pi square by 2. 1 by norm k square. The equal to is also k reverse. And here we have 1 by 5k dk. And here we have 2d by log of k square dk, and we will the corresponding integrations. Nice. Now in this integrand, the function we have is 1 by, it looks like something like 1 by mod of x square. Okay. And this particular function takes values from positive real numbers and maps them to the positive digits along with 0. Right? So in this case, now we can transform our integers into desirable format, and that particular format will be d by pi square times, here the limit of the integral was from minus pi to pi, and we have volume of this power d minus 1 times 1 plus r square power d minus 1 d minus. So this r power d minus 1 term, this basically comes from our Jacobian matrix of the transformation, and this is the volume of the d-dimensional sphere. Okay. And as this function we have here is even function, we will basically write it in this way, and after taking all the constant aside and determining the number of c, we are left with something like this. Okay. Now this particular integral is a finite answer if and only if b is greater than or equal to 3. Otherwise the integral over here will be divergent. Okay. So if the integral, this original integral diverges, the thing over here also diverges, and similarly g of 0, 1, which we have already listed before, that thing also diverges. Okay. And similarly, taking the other bound, we can show that for only d is equal to 1 and 2, this random one will be converted, because for only that case, this particular integral will be equal to infinity. So g of 0, 1 will be equal to infinity, and from that level we have proven earlier, the random walk in that particular dimension will be recurrent. Okay. So in this entire talk today we have explore that the recurrence and the transience of these systems is actually kind of chaotic. I mean, this only depends on the dimension, but if we change some certain conditions, like if we introduce bias or if we introduce some certain kind of resistance or conductance, then this result may change also in some cases. And to conclude this talk, I will just say a famous quotation by mathematician Shizuo Kakutani and many others, that a drunk man will find his way home, but a drunk bird may get lost forever. That basically means that a random walk in 2 dimensions will eventually return to his home or to the origin. But a random walk in 3 dimensions might be lost forever. And this also justifies the merchandise that I am wearing to all the first year students. And thank you. Thank you very much for listening.
Try to find out